topic is how AI allows complex phenomena to harmonize with creative arts. Let's welcome.
Yeah, thanks for the introduction and thanks for coming to this talk, everyone. Yeah, I'm Byungsoo. Today I'd like to talk about how AI allows complex phenomena to harmonize with these creative arts. I'm currently working at NVIDIA in Switzerland, but most of works covered in this presentation was done when I was doing PhD at ETH Zurich. So let's start by looking at the traditional lines between science and arts. So in the past, these areas were seen as separate ones, with, each with its own methodologies and objectives. But now with AI, we are seeing them come together. Technology's analytical power is mixing with the human creativity and creating new ways to explore and express art. So these days we create digital contents which is believable and compelling virtual worlds. Then a natural question arises: how can we make the digital content convincing? And one key point is realism. As seen on the right, we are easily captured and convinced by photorealistic appearance of digital avatar character here, even though it's not a real one. And that's not the only factor. Human perception is also super sensitive to the motion. So physically plausible motion is another essential part of the realism. So speaking of motions, let's have a look at these three different types of motions in creative arts. Character animation is one category representing the motion of inhabitants such as humans, animals, or any artificial creatures. And those characters typically have hair, fur, or cloth, or even flesh. Like these things need to be animated as well, which is called secondary motion, since it follows the primary motion of character animation. And lastly, the world itself consists of physical structures such as fluids, rigid body, elastic materials being animated in nature. So for simple motions, people can just draw it by hand, but it will be, infeasible for complex physical phenomena. And that's how the physics-based simulations are introduced in this field. So, over the last 30 years, physics-based simulations have been progressed and widely used to create realistic motions of digital contents. You can see like splashing water, smoke, or cloth, or even pizza as well. So I'm from Switzerland, so I just wanted to show some pizza here. So I don't know how many theoretical scientists would care about making digital pizza or baking fake breads, but it's quite important for us to make digital content like this. So how do we do this? First, we need to derive the mathematical model first. Think of this as a blueprint of our simulation. So let's say we wanna simulate water, then we will pick sort of the incompressible Euler equation, for instance, as a the mathematical model. Then next we implement the computer model. For instance, decide which kind of representations, spatial discretization we should use for, such as like grid, particles, or both. So once we implement all of this, then we can run it and grab a coffee. Then what are the main challenges here? First of all, is physics simulation. So we should solve the right equation in a correct way. When pouring water, then the volume, the mass shouldn't change because it's water, right? And physics-based simulation is computationally super expensive usually. But we don't need a weather forecasting level of accuracy and can't wait for several days just to see water goes into the cup, right? So it should be fast enough so that we can balance between the physical plausibility and computational efficiency. And lastly, we also need to secure the art readability as well. We need reality, indeed need a reality, but we need to go beyond it because reality is actually boring as a digital content. So therefore, controllability of simulation is another key challenge. So now let's talk about how AI technology can help with these challenges. So these are main contents of the presentation. So I'd like to briefly go through in these three major ideas in learning and physics. Uh, First of all, like typically, an analytical model is implemented in physics engines for accurate and stable prediction of complex dynamics. But no matter how well implemented they are, those analytical model systems suffers from reality gap due to the error of modeling or entirely unmodeled effects. For instance, we can build a idea like a quadrant robots for simulation, but it's not easy to model all different kind of frictions in their joints and contacts in real world. Thus, several learning-based approaches have been proposed to replace analytical model. So let's have a look at this data-driven model first. So the basic idea of data-driven model is demonstrated on the right. Using a bunch of simulation data, we train the regression model to predict the next state of the dynamic system given the current state. Then during the test time, we use just this trained regression model for time integration at cost. So once a surrogate model is built for solving fourth problem, it outperforms traditional solvers by orders of magnitudes in terms of runtime. Also, we can reduce modeling error or learn unmodeled effects from real-world measured data directly. A data-driven model is also used for the ill-posed problem analysis. So for instance, GAN approach is applied in the context of super resolution of fluid simulations. Interestingly, it could upsample given low resolution flows in both spatially and temporally coherent way. And another example is like flow data reconstruction from satellite observations. Measured data from real world typically has some missing parts or degraded by sensor noise or resampling artifacts. So in this work, physics-aware neural network is proposed solving an inverse problem of fluid, flow inpainting or robust noise filtering. So in this sense of data-driven approach, I would like to introduce our work on generative fluid model. So title is Deep Fluids, a generative network for parameterized fluid simulations. And this work is the result of collaboration between ETH Zurich and Technical University of Munich and Pixar. So the underlying motivation is like this. So there are tons of simulation data in Disney and Pixar generated during film productions. And it accumulates over and over, but mostly they're just there. I mean, it's really hard to reuse. Just artists usually just set up all the things again and then simulate. So we want to find a way to effectively store and reuse them. So that was the beginning of my PhD. So for those kind of problems, traditionally, data-driven technologies like the model reduction or reduced order model have been proposed to speed up simulations. So basic idea is to design a projection operator to the manifold in the subspace and demonstrate the time integration at cheaper cost, then reconstruct them back. So in this work, we tackle the challenges of reduced order model, which is basically for fast and accurate projection to the subspace, integration, and reconstruct them back to the real space with the full space with the help of deep learning. And we propose the first convolution neural network that fully constructs dynamic Eulerian fluid simulation velocities from a set of reduced parameters. basically the idea was to have like a super overfitted network on this fluid simulation data. And once the network is trained, we could achieve the performance speedups, compact representation with nonlinear interpolations. And lastly, we describe a novel latent space integrator for the complex parametrization. So let's talk about subspace construction. One way we can do is just build a reduced parametrization by dimension reduction for manifold learning like PCA, SBD ways. But actually, we realize that the many scenes are inherently parameterized from its initial state. So here we show the videos of several example scenes used in one of our training data sets. So in this example, we vary the inflow velocity and the buoyancy of a smoke source traveling horizontally on an open container. So its intrinsic dimension is 3: inflow velocity, buoyancy, and time. And due to the inherent nonlinear nature of the Navier-Stokes equations, these 3 parameters already create a collection of widely different simulations. So to learn it, we implemented a simplified architecture. The model takes a set of reduced parameters and output velocity fields, which is very typical CNN structures. But this part is a little bit, designed for this special purpose. So we added the linear transformation layers to the end in order to intrinsically work with the stream functions. So I'd like to talk about this, the importance of domain knowledge for this kind of learning task. So imagine we have data collected from this multimodal function y squared equals to x, like bunch of coordinates 1, 1, 1 minus 1, 4, 2, 4 minus 2, for instance. And we simply train the network with this L2 loss, then well, eventually they will just converge to this flat red line, like weak failure. Right? On the other hand, let's say we have already have some knowledge of or some hints by looking at those data and found some underlying model, for instance, then we can do a much better job. So for instance, change the loss function to compare the x and y hat square, then it can at least to capture one models of target distributions. So in the similar sense, we here train on the velocity data from the fluid simulation. It's important to satisfy the physical constraint. In this case, we need to enforce the incompressibility onto the network output. And previous approach added this divergence term to the loss function as a soft constraint. But the problem is that it never goes to the 0 at test time, even accumulates over time integration. So how can we do this? How can we do a better job? So if we have a better knowledge of domain, we can use it as mentioned. And divergence of curve of any vector potential is always 0 by definition. So now then we can just decompose the generative model into 2 steps. And then output velocity field is unconditionally divergence free. So with a teaspoon of domain knowledge, there is no need of divergence constraint nor ground truth stream function for training. We still use the ground truth velocity field as before, but now we don't really need the constraint for it, but we can guarantee the divergence free velocity field as output. So this model-based and data-efficient training has been developed in recent years. It eventually allows us to train with the partial differential equations directly instead of supervised loss. It's called the physics-informed neural networks and combined with differentiable physics afterwards. And I'll discuss it later. So let's see some interesting results of our method. So in this video, our model reconstructs and interpolates on an obstacle position. So our model could reconstruct the velocity field pretty decently, but also could give nice nonlinear interpolations. This is possible since CNNs can naturally learn the nonlinear interpolations between sets of input parameters. Our method also can handle liquid simulations, which was not possible by traditional methods due to the nonlinearity on its interface. And in this, in the middle, we interpolate on the distance and the angle of two liquid spheres, and our model reconstructs a new in-between parameter point. However, scenes not always parameterizable. Like one example of scene with the difficult parameterization is this moving smoke scenario. We could parameterize these simulations by the history of all its source positions in time, but that would increase the parameterization space over time, which makes the training unfeasible. So for this kind of unfeasible cases, we use autoencoder to have a reduced representation. So below, we show some example of consecutive latent codes, which represent the state at the time t-1 and t. And time information will be diffused in the latent space once it's trained. So thus we need to know how to advance time in the latent space. So we designed a novel latent space integrator which helps navigate how to go from current latent space code to the subsequent one. And as a result of extended parameterization, we could successfully handle new source motion that the network hasn't seen before. And this performance table shows that our method achieved up to 700 times performance speedups compared with underlying CPU servers. And our method provides a powerful compression algorithm for fluid velocity fields, improved on the state of the art by the 2 orders of magnitude. So that was kind of basic idea, which was done in 2000, mostly in 2017. It's quite outdated work, so we also did some follow works on this as well. And so yeah, as I mentioned, we talked about learned physics, and then we wanted to extend it to to make some extend it to the digital content creation area. So this is one example. Filmmakers and video creators often use this kind of storyboards to transfer ideas from their mind to the screen. And this was a very interesting example. In production stage, the film titled Raiders of the Lost Ark in 1981 by Steven Spielberg. And it was illustrated, this storyboard was illustrated by the Ed Farouks. And let's see how closely they guided the final film, imagery. And we see the great use of sketch and shading in storyboards to represent a mysterious energy stream around, but they are used for the purpose of communication rather than a final visual realization of 3D flow. So our question was, can we transfer these concept sketches directly into a volumetric flow structure? So here in this work, we presented the first method to compute a 3D smoke density field directly from 2D hand-drawn sketches. So for this one, can imagine we can train the network. Once we have this, input and output data sets. The problem is it's hard to, collect this kind of artistic sketches on top of this fluid simulation data. It would, we have, let's say, 1 or 2 artists, they can draw, I don't know, 5 to 10 sketches per day. Then to train the network, I don't know, 10,000, 5,000, 10,000, 20,000 fluid sketches. I mean, it would collect, it would take forever. So what we did was just to implement a differentiable sketcher. So once we have, we can generate the corresponding sketches on the fly for the end-to-end training with this differentiable sketcher. So our method is inspired by the absorption in a smoke rendering and estimate the normal map. And we average the normal map for a range of density isosurfaces at the visible boundary of the smoke. Then contours are extracted, followed by the to the cartoon shadings and so on. And this is one example of interactive authoring. We ask the users to, just draw it and then use our plugins to generate the smokes from those kind of sketches. Another example that the work that I liked was this one. So actually, this is just a motivational, like a teaser. I inspired by this Netflix series, and then just directly move on this project. So when we see this, the smoke monster. I mean, the Netflix title is like Hellbound, and those are like monsters from the Guardians, like a Guardians of Hell, to bring you guys to the hell, basically. And they're like, they're cool like smoke effects around the monsters, and I wanted to do the similar things, but in a more efficient way. So let's say we have to make this kind of simulation, make this kind of effects. We need to do the simulation on top of the character motions. But what if we just do the simulation once on this T-pose like a character, and then just deform it according to this character animations? Once we deform it, then the physical plausibility will be just broken, right? So which means here, like if we do the simulation, the simulated data will on top of this Navier-Stokes manifold. But once it's deformed, it'll be just kicked out of this manifold, and we wanna project them back to this Navier-Stokes manifold in an efficient way, which is like called the neural corrector that we believed in built in this work. So you can see this is the original simulation that we just simulated once, and we wanted to make a new simulation just by deforming and correct it in an interactive way. So you can see that once it's just deformed, you can see lots of artifacts, probably not physically plausible as well. It doesn't go away, just pretty weird, but could correct it in a more physically plausible way. Another follow-up was like just to improve the quality of the last work and the deep fluid. So the idea of deep fluid was to have like a structured manifold for the physically plausible time integrations. But if it's more constructed in a structured way, then we believed well, we can have more stable subspace integration in a long-term way. So we try to subdivide and then put some constraint to have more structured latent space so that it can have longer stability in time. And we also reinterpreted this problem as like a navigation in the Navier-Stokes manifold. So we also try to learn how to navigate in the latent space using this deep reinforcement learning way. We also found a very interesting use case of our generative model in another field. So this figure shows an example of electromagnetic navigation system. So the basic idea is, let's say there is like a micro robot, and to handle this, let's say some surgical purpose, they need to generate this magnetic field from the like very few dimensional current, which is like 8-dimensional, for instance, and then it should make some sort of like 3D magnetic field, which is divergence-free, should be divergence-free as well, and was the perfect use case of our model and showed a very nice use case as well. And also we could extend our work to the field of glaciology as well. I mean, we live in Switzerland, and there are some scientists want to work on this, flow modeling, ice flow modeling as well, and we could extend it as well. So far I have, introduced some of the works in the sense of, like a data-driven model for having a fast and model-free, also to solve some ill-posed problem analysis. And there is another advantage of using this kind of model, which allows us to have like synergistic combination with other deep learning models. And let's have a look. And yeah, so the title of this work was the transport-based linear style transfer for smoke simulation. So in this work, we propose a novel method to synthesize semantic structures onto a volumetric flow data. Our method enabled the general content-aware manipulations ranging from simple patterns to the intricate motifs. And our method was also able to transfer features from the paintings or natural images. And in this way, simulations can be artistically manipulated by many different styles and templates, enabling novel stylizations that were not possible by previous approaches. And luckily, well, this method could be extended to apply to this, the recently released the feature film called the Elemental, and this technique was applied to this main character, like Amber. I don't know if you have seen this animation, but so once you simulate the, let's say, like the fire for simulating this kind of character, then it looks too fiery to too fiery. It doesn't really look like a character. So the artist wanted to have the full control on the appearance of this character, and then our method gave some used as some sort of like solutions. So here we show two categories of our results. Like on the left, we see a flowery smoke generated by semantic transfer, and on the right side, we see a stylized smoke, 3D smoke structure by fire reference. And I'm going to detail the difference between them. So let's imagine there is a score function that can, measure the floweriness of given image. Then we can make the flower smoke by somehow maximizing the score of the smoke. And this is a close-up view. Note that there was no reference image of flower used here. We just maximize the score of certain semantic, in this case flower, and we call it semantic transfer. Well, semantic can be anything. For example, espresso. This is cookie dough, and this is soap bubble. And you see some crema patterns on the espresso smoke, and the crease of dough and the filling of soap bubble here. So semantic transfer gives a general look and feel of certain semantic automatically, so the artist can avoid the tedious handwork. And second application is style transfer. You might want to just, so smoke looks like a fire. You could give a fire example. And unlike semantic transfer, it requires a reference style image. So in this case, we need to extract style of given image, which is defined as like repetitive common patterns. And we match the style of smoke with it. And our stylized smoke shows fire style while keeping its physical characteristics. So how can we extract those semantics or style features? And Algetis et al. Firstly proposed the artistic style transfer by extracting two separated features, content and the style. When convolutional neural networks are trained on object recognition, they develop a hierarchical representation of given image dataset. So along the processing, the hierarchy of the network, input image is transformed into some representations that increasingly care about the actual content of image compared to the detailed pixel values. And those extracted features are called the content feature, containing different level of semantics. Like at the first layer, they see like high level, low level, like semantics, like texture, like a common appearance patterns. once it gets deeper, it has more complex or combined patterns. It becomes like in parts, and afterwards, it represents some objects. And then from those content features, we can compute the cross correlation between them by taking outer product. And it captures the texture information, which is a stationary image representation. So we can obtain multi-scale texture information as shown in the image below. And from left to right, you see varying levels of texture styles, and they call it style features. So just to better understand our method later, so let me examine the original Eurostyle transfer for images here. So with the initial source and style images and target images, and here the target image is initialized as noise. And then target image filter response is computed by the image classification network and iteratively optimized to both match the content of the source and the style of the image. And since this pipeline is differentiable, well, this optimization will produce the per pixel corrections that will yield the stylized image that preserve the original content. But well, we couldn't directly extend this method. There were like 3 main challenges. First of all, the naive NST implementation would lead to the uncontrol of the density source and sink. Secondly, we handle the 3D smoke volumes, and those are just designed for the 2D features. And lastly, if we just stylize it, there will be like heavy temper flickering like that. So, naive NST method will result in an arbitrary density creation as there is no constraint for density control. So, you see, this is not natural or physically plausible. And maybe we can do some masking as well, but it just restricts the area of stylization, not the amount of density. So to avoid the density control issue, we proposed a transport-based Eurostyle transfer, where the stylization is driven by velocity field, just like fluid simulation. So now the original objective with respect to the image I becomes the function of velocity, density d and a velocity v. And backpropagated gradient will update the velocity instead of the original density field. Well, however, if the density field is 3D, we can't directly plug in an advected density to the loss network, which only takes the 2D inputs. So to handle that, we implemented the lightweight smoke renderer, differentiable smoke renderer, to get a 2D representation of stylized smoke. So the objective is change it to include rendering functions accordingly. And one important thing is that our pipeline is, as I mentioned, is based on the gradient gradient descent. So for optimization of velocity field, so rendering should have to be differentiable and fast enough. And finally, we tackle the heavy temper flickering issue. Basic idea is that we already have underlying velocity field from the simulation, so we could use it to like a temporally smoothing the generated stylization velocity fields. And this is a semantic transfer result. So we could transfer net structure on the left source smoke. Here you can see more intricate motifs, cloud patterns, and this is a stylization wizards. You can see some Picasso style or some loop print style strokes on top of the smoke. So our approach was flexible enough to accommodate the artistic and photorealistic stylizations. And we extended that work to the main limitation was previous approach was, the like computational expensiveness as well. Like we had to spend like a day to make this kind of things, but wanted to reduce the computation time. So we switched the representation from grid representation to the particle one. The basic idea is in the middle of the pipeline, we split the particles to represent the underlying the grid structure, so that we can reduce the runtime from 1 day to like a single hour. Also could extend it to the stylization of liquids as well. Yeah. So far I've talked about data-driven models, which can have like a fast and again model-free ones, and can be make some great synergistic effects with the other linear network. But well, black box training always doesn't lead to the accurate one. I mean, usually not as accurate as in general as an analytic model, and that's kind of big problem of this data-driven model. So yeah. During the success of learning physics, the other types of simulator has been growing, called the hybrid physics. So the physics network is plugged into the analytic model for replacing or augmenting the part of the analytic model. And another ingredient of this hybrid model is differentiability for end-to-end optimization of either simulation parameters or physical network weights using the gradient descent. And without differentiability in an analytical model, lots of iterations were demanded to find the best fit to the real-world observations. So here, this is a very interesting example. So with the differentiable, so they could build the differentiable water wave simulator, and since this is a differentiable, they could optimize the initial weight height field to break this the VGG network, for instance, basically. So here VGG network classified this as a like an image of squirrel, but this is like an adversarial optics. So by putting this wave effects on here, they made the VGG to classify this one as like the goldfish or some other objects. So with this differentiable simulator, it's possible to optimize with optic in that sense. So yeah, in the sense of hybrid physics, we also worked on a facial expression simulations as well. So let's just describe the problem here. Let's say we have a set of parameters omega of interest, and let's say we have a differentiable simulator which generate the U star, the outcome of the simulator. And these parameters will be fed to the simulator to generate the U star, and we have, let's say we have like S, like a target simulation or physical quantities, even can be captured from the real world, and then can put it into the loss function. Then since it's a differentiable, then we can optimize the omega, the simulation parameter, to match to the measured like real world data. So now here, in the case of facial expression simulation, omega can be the underlying muscle values to be optimized, and output of the simulator would be the deformed face controlled by the muscle, and the target can be like measured, capture data. And the loss function then can be used to measure the geometric difference between them. And after optimization, we can further faithfully add other physical effects while keeping the expressions like the collision handlings and then secondary dynamics as well. And this generally inspires a recent interesting work while they were in a low dimensional latent space lambda. and sample the fine-grained actuation tensors from this space with the network. You can imagine this lambda as some sort of like expression factor, let's say happy or I don't know, some sad or those kind of very low-dimensional like expression latent code, which generate all the actuation tensors on the face. Let's say here, this is like a front part of the face. And yeah, so the Srinivasan et al. In 2021, they built a neural network which could generate the actuation tensor values to, which can afterwards fit into the differential simulator and can have differential pipeline to have like eventually like an expression code. But the problem is in this work, we typically use the high resolution like a simulation face match, which has like a 250K like a triangles, for instance. And the last layer of the network should be compatible with the resolution, which means last layer can be like billions of parameters without any architectural like customizations. So yeah, we extended this work to by incorporating the neural implicit representations, which is representation discretization agnostic, so that we can just easily plug in any type of resolution meshes to handle the this facial expressions. And this is the result of our work. So you can see this shows the like actuator is just represented as like a cube, and the intensity of the deformation is represented as the colors. And well, we could match to the capture data by optimizing the learning and then optimizing the network, which gives the proper actuations. So yeah, so in this talk, I have introduced some of our works in the sense of learn physics and some high-level physics, and those kind of models have pros and cons. But well, we could find some good ways to use that for digital content creations. And yeah, that concludes my talk. And thanks for your listening.
Thank you very much for, again, a very exciting and useful talk. And do you have any questions? Any question here?
So how the neural network recognize the style of how do you define a style of an image? Why how the neural network can recognize the styles?
Yeah. So that was the interesting part actually. I mean, I didn't invent that part, but as I, let me just. So, I mean, Gettys and the collaborators could found that once you train the convolutional network for the object recognition, and then feed into that network, and then they could found that there are some interesting informations. I mean, of course, we can imagine that those network is trained to extract the interesting features to recognize what's in there, what's in the input image, right? But they could go further that from those features, and then they found that the statistics of that feature could represent the styles, and that's how they define the style features. I mean, here they use the second order statistics, which is the outer product of the flattened features. But if actually you just the mean and variance of these feature maps, while generated while feeding to this network, already can represent the style, which is defined as like a stationary image representation.
Okay, thank you.
Yeah. So in some style, it's kind of statistics of features, which could be extracted from the while feeding to the network.
So it's different from the 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 frequency different
Frequencies?
of the image.
Yeah, it's a little bit different. I mean, let's say this is a stereo night example. And this is not just about like a frequencies, right? Of course, if we go into the deeper network part, we see some in the high frequency part, we usually in the top part, and low frequency part, like a high level semantics will be extracted from the lower, like a deeper part of the network, right? And from some statistics of those features, it could represent this kind of high level ones here, and some stroke style, and some more general style, or some at the end is more like a color styles as well. So it's not just the frequencies; it's more about like stroking or some common patterns, not just restrict to the certain area, but it's more like a general statistics of the in frequency area.
Okay, thank you. Thank you very much.
Okay. Do you have any question? Anyone? Okay, maybe I will ask you a question. So about I hear about that you're using gradient descent type method for training the neural network, right? So among many variants of the gradient descent method using stochastic something like that, and what exact method you are using? I know what the reason.
Well, it's been a while since I implemented that one. I think I just typical one like use the SGD or something with this Adam optimizers and so on.
I think the type or something like
Yeah, at the time, still I had to use like TensorFlow. It was like early work, so TensorFlow was more like a famous one at the time, like 2016, 17, and then after that I switched to PyTorch.
Yeah. Okay. And not something accelerated method, Agama, something like that, or just a classical one?
Actually, in those work, we try to avoid some special like tricks, like to avoid the over engineering, so that we can just focus on the method. Okay. And afterwards, we had to push a little bit the boundary, like the finer accuracies or appearance, to get the better appearance. But afterwards, we try to focus on just method part, not just engineering part.
I see. Thanks a lot.
Hi, thank you very much for the speech. It was great. I have a question about the training time and volume of data. How much time more or less did it actually take to get this thing working so good as it
Yeah,
is?
so that was a good question. So I mean, it answers to. I mean, it reminds me of very hard time during my first PhD. So at the time, I only had like one 1080, which has like 8 GB of memory, and mostly because of and we focus on the dense representation of 3D data, which I mean, in that case, the memory was like bottleneck. So with the 8 GB of GPU, we could go up to like I don't know 100 cubic 100 cubic resolution for the velocity field. So and had to train like almost several days, like up to a week, for instance. Like there were like 10,000s of velocity fields as a training data set. That's in the case of extended parameterization. And with one GPU, we had to spend almost a week just to train on those like moving torches scenario. And we couldn't go over 100 cubic resolution at the time. But nowadays, I mean, there should be much more efficient, representation, like sparse representations and, many parallelized techniques as well. So I think now those like scalability issue are, well, lifted well, I guess.
I have another one. I really like the idea of the incompressibility property of the materials. How beneficial was that compared to just do it like?
Sorry?
Yeah, you said that you added the uncompressibility property of the material on the loss.
Yeah.
That was adding like a physics to the problem. How better was the performance of the model once you added that?
Oh, so without compressibility, once you like advect the smoke, after some time steps, so you will see so many kind of dissipations of the smoke. And with those, constraint, of course, so you will preserve the advective densities, which will be, after some time steps, you see much more smoke. I mean, I didn't include it in this slide, but in the paper, I showed the comparisons with and without those kind of constraints. And most of them are was visually, noticeable.
Yeah, that was a bit the thing. Like, I get it how the water can't be compressed, but with the gas, with the smoke, and you have Euclidean like grid, as you said, like the density is not constant across the grid. So how does the incompressibility restriction improve the performance of the gas if it's actually not being like spent?
So yeah, I mean, it's about the underlying velocity field. So if the underlying velocity field is not divergence free, which means there will be some sort of like source and sink, and it basically results in the dissipation of smoke. Is that the answer to your question?
Yeah. Okay. Yeah. Thank you. Thank you. Thank you very much.
Okay. Anyone have any question? That's fine. Okay. Let's thank again Professor Kim for excellent talk.
Thank you. Thank you.